Thank you. Okay, sounds better. Very good. So I would like to start with the take-home message. So if you don't want to listen to the talk, I perfectly understand. But I would still like to take something from this, and I think this is also the leitmotif of the conference, and can be summarized really with this sentence. So when the complexity of the problem becomes very complicated, so increases, look at simple recurring structures. So as Lorenzo has already mentioned, what we are trying to do is really to phase the so-called percent level phenomenology program at the LSE. And this really relies on our ability to interpret and predict the outcomes of the LSE. So, of course, a process at LSE is something extremely complicated, which involves different energy scales, different effects, and I mean, is not an easy business. Fortunately, we can separate these energy scales, and each of them can be treated separately. So my job is actually to focus on this small part of the calculation, which can be tackled using perturbation theory. So, and actually this is something useful to do, especially when there are no large hierarchy scales in the process, and observable we are interested in is not extremely sensitive to infrared physics. So under this assumption, the so-called fixed order predictions provide a very robust and reliable framework to obtain a precise prediction at the LSE. And as you can see from this plot, a lot of effort has been devoted, and all the audience here can testify, are part of this progress in increasing the number of loops and lags that we can account for. So talking about precision, of course, if we use a very simple power counting argument, so as Lorenzo already did, assuming the strong coupling to dB 0.1, we immediately understand that next to leading order is mandatory to match the required precision. Indeed, order alpha square is about 1%, based only on power counting arguments. In order to do it, we need several ingredients. So most of you are interested in this part of double loop, double virtual corrections. I'm not so smart, so I look at the other part. And I just want to stress that each of these ingredients require actually a lot of effort and to overcome technical challenges, which require in turn a profound insight from quantum field theory. So as we all know, virtual amplitudes are complicated because they involved loop integrals, including many scales, masses, lags, is a very difficult business. However, also real corrections are not that easy, although it's, let's say, sometimes it's assumed that they are straightforward. So let's take a closer look at the problem. It's very simple. So look at a very simple Feynman diagram. You have learned at the bachelor, I guess, how to write the Feynman rules for this. And you immediately realize that under some limits, called soft and collinear, this object simply blows up. In physics, it's not sufficient to say blows up. We have to quantify this blows up. And we can do it in dimensional regularization. So the point is that these singularities only become manifest after integrating over the phase space. And they becomes explicit poles in epsilon using dimensional regularization. So far seems there is no problem so far. However, the crucial point of my job is trying to extract these singularities prior to the explicit evaluation, so retaining the fully differential nature of the calculation. So the idea is pretty simple and is based on a fact that the unresolved limits are universal and known, and therefore a general procedure is at least in principle feasible. So the idea is this one. So we start with a very complicated quantity. We subtract from it its singular limits, such that this is by definition, so by construction actually, finite in 4 dimensions, and we can use a computer to compute it. So since this is an equality, what we have subtracted, we have to add it back. And we can understand that this quantity is simpler than the initial one. So this we can hope to calculate analytically and get the same pulse as the one that we will combine with the virtual correction. Actually, despite the sketch is very simple, in practice this is definitely non-trivial. However, if we retain some good properties like locality and analyticity, this method seems to be very flexible and gives us a numerical stable result. So yeah, the sketch is easy, the practice is not. Very good. So indeed, this problem, So the problem has been solved at next leading order when I was born, so quite some time ago. And at next, this is still an open issue. So it's not always true that the virtual is the only drawbacks for high precision. And indeed, if we look at this very simple example, to move from amplitudes to predictions took almost 15 years, so it was not definitely trivial. On the market, we have different solutions based on different principles, a large variety of them. I work on a scheme that is not actually the one that I'm going to present you. And apparently, most of them have some intrinsic difficulties in going beyond next leading order for arbitrary processes. So what the point of my talk is that we are trying to find some simplifications and recurring structures that can be elusive given the difficulty of the scheme or the procedure one has to deal with. Good. So why it is so difficult? In principle, one can also write a very simple diagram for this case, but then you will immediately realize that this is much more complicated than before, and many other singular configurations arise. So first of all, one has to decide very clearly which configurations do actually contribute and get to the point where the problem is well defined. And at the end, we have to also solve the phase space integrals that, as I mentioned at the beginning, have to be taken and combined with the virtual. So just as an example, you can see here that in order to have a zero denominator, you also have to account for these so-called energy ordered configurations, so these strongly ordered limits. And the kind of functions we have to integrate are of this kind. This is a double soft that we have to integrate over double unresolved phase space, possibly with some constraints. So far, so good. So the way it is done in nested, which was first designed by Melnikov, Kaula, and Ronst in 2017, is pretty simple. So the slide is a bit convoluted, but the principle is very simple. So you start with the soft, you extract them such that you have something that is clearly divergent from something that is clearly not divergent in that limit. What is clearly divergent, you integrate analytically. What is not, you keep going subtracting the remaining singularities. So somehow you go layer by layer. So the last step of your subtraction procedure is due to the collinear singularities, which are the most involved one. And here you make use of some very well-known techniques, meaning the introduction of partition functions and sectoring. I don't know why it's so blurred, but okay. Very good. So what I'm trying to say behind it is that the procedure is very well established. And in order to integrate, Melnikov and collaborators actually use reverse unitarity to map these phase space integrals onto loop integrals, which can be familiar to you. So all the techniques more used to the amplitude community. So does this work? Actually, yes, has been tested with some processes, which, however, have something in common. As you can see, they have at most 2 colored partons at leading order. What we can do now, what we were interested in, is actually increasing by 1 this number of colored partons. And why do we want to do it? Because this is a good prototype for a fully generic scheme. So we do one step further and hoping for getting for free the most general case. Very good. So we do the exercise. We take the original, let's say, method designed by Melnikov. We write down what is for our case. And despite all the details that are not interesting for you at all, the point is that we are able to write two blocks of terms, one collecting all the singularities, the explicit singular contribution that we have to integrate, and one collecting exactly all the finite remainders that we want to integrate numerically. So in principle, there is no such a mystery behind this formula. I just want to point out that this is done for just a few partons. And you can spot it looking at the indices of the sums. So if I increase the number of partons, these sums will become much, much longer. But the general structure will stay the same. So where is the problem? So far, seems everything is okay. But when you move from the formula to the actual calculation, it's a nightmare. So first of all, the bookkeeping is going to kill you immediately, given that the number of subtraction terms grows very fast as far as we increase the number of legs. Moreover, the initial strategy was to compute each of these terms separately, then put everything together, ask Mathematica to simplify, and hope for a cancellation. So we realized pretty soon that this is not the best way to do it. And we were instead trying to find a number of simplifications that can occur before the explicit evaluation. And in order to have an idea, I'm sorry, but there is no point to see all the numbers. If you ask Mathematica to expand all your counter terms, she will complain. If you ask her for the virtual, she will say, okay, sure, okay, it's a few lines, amazing, very beautiful. So since these two objects have to combine and simplify, why this is so complicated and this is not? So our job was essentially based on this question. Can we identify structures that appear all over the place and infer cancellations by eye, so without really forcing a series expansion and a simplification? And the tricks here seems to do what exactly is the opposite of the standard procedure. So instead of taking the real, looking for the limits and get the counter terms, we started with the virtual, which we know in its infrastructure, and infer the form of the counter terms. So this has been a preliminary study in a very symmetric configuration, and we are working at the moment together with Federica, who is in the audience, and others, to extend our method to more general configurations. So let's start with something very simple, and next to leading order. Again, this is just as a warm-up. And I want to convince you that the strategy is very simple, very trivial, as soon as you get it. So you write the cross-section in terms of virtual, a real, and a PDF contribution. You know exactly how the virtual corrections look like in their pole content, and they look like this. They are regulated by the Catani operator. Then you take a look at the real, and you start organizing it in terms of functions that I will call IS, IC, and something else, which actually have properties in common with this I1. And indeed, when you combine this quantity, you will immediately realize that the IS pole trivially cancels, and color correlations also. The remnant is exactly given by the collinear component proportional to the elastic kinematics. So we were able to identify a structure, this IT, which is finite and free of color correlation. And therefore, we were able to write the cross-section and next reading order really in one line. Okay, so the problem is, can we take this lesson and do the same at next to next? And the answer is more or less. So the guiding principle is take the virtual and try to find the corresponding quantities that can complete the IV. So actually, we started from this guy and we're looking throughout the calculation for its partners. And you can see that the virtual is not a random function, clearly. So it has some dependence on this IV operator, but we were guided by some properties like different powers, different arguments, different prefactors like beta 0 or whatever, and different color structures encoded in this formula. So we were following the color structure to actually get to the point where we were able to retrieve this combination. I will show you a few examples. Don't focus on the details, just on the message. If you look for color correlations, better for you to look at the double soft and soft real virtual. So just to show you an example, if you take the double soft, which is given by something like these diagrams here, it is made of two different contributions proportional to two different kind of color structures. And actually, the factorized term can immediately be written in terms of this IS with exactly the same power that we need to complete the virtual one, and therefore taking care of the quarti-color correlations. So I will take a step back, one, hopefully. Sorry. Okay, so you see here, we have IV square with 1/2 and so on, and we get exactly the corresponding structure here. The powerful of this method can actually arise a little bit more clearly if we look at the non-factorizable term. So this function is actually the one that I showed you before that was looking nice and simple. If you integrate it, as they did in the literature, you will get a bunch of ugly functions and numbers, and so nothing particularly inspiring. However, if we insist in trying to reduce all these functions to a set of recurring structures, we will understand immediately that this can be written, at least in its pole content, in terms of another function that is really related to the one that I was introducing in next to leading order. And again, also here we are guided a little bit by the prefactors and the color factors sitting in front. So real virtual, in this case we have a loop and a real radiation. This is the form of the soft limit. And once integrated, again, we were insisting in finding these structures all over again. So what's the point behind it? The point is that at this level, you start seeing a pattern arising, right? So on top of the details, what I'm trying to convene is that in the past, the main strategies was to take all the different ingredients, so double virtual, soft double real, soft real virtual, and so on, compute them entirely, and then combine everything together, simplify everything, a bunch of ugly numbers, and get a cancellation. What we are trying to do here is actually looking at the columns such that we're able to get to the point where we have our IT function, and we know already that is finite. We don't have to recompute it again and again and again. So I will show you one example, and then I will conclude. So if we take into account also some selected collinear contribution, we will see that the virtual plus the soft proportional to the elastic kinematics will look like this. And the important point on top of the details is that in the first line, you are able to recognize by eye this structure over here. And again, you can already claim that there are no singular color correlations without computing it. Okay? So to conclude, I hope I convince you of some results. So I started with a question. We had some knowledge about a procedure that was very well tested with simple examples. The question was, can we generalize it? And the answer seems to be yes. And the trick is to find next reading order universal operators that describes the different types of singularities and combine them into finite quantities. So this is a little bit the summary of my next reading order discussion. This object is free of pose and fully general in the number of finite state partons. At next to next, the trick is to find iteration of these operators such that we can prove the cancellation prior to the evaluation of these counterterms. So this is a little bit what I was trying to convince you about in the last slides. So this is the standard conclusions then. I hope I convinced you that real radiation are interesting as much as the virtual corrections, and they are necessary ingredients to obtain very precise theoretical predictions. We have a method that we took from the literature, but we boost it. And now I think we are ready to get rid of a generic process. We have already succeeded in obtaining a finite result in the case of n gluons, so QQ bar into n gluons, and checked the final remainders against the old-fashioned way, so the very standard procedure. What we are trying to do is actually face in some technical issues related to less symmetric processes, but this seems very promising. And with this, I would like to thank you for your attention.
Thank you very much, John. So we have time for questions. Anyone wants to start? Okay. So maybe then I will start. So I understand that somehow the virtual corrections provide the guidance for your treatment of real.
Yes.
And I understand that the first element there is color, right? That's
yes, we were guided by color structures. So the point is that for the first time, we were trying to organize the calculation, really splitting the terms according to some properties, general properties, like color, kinematics, and so on. So while before it was, let's say, less transparent. So we really tried to enforce these properties and really look for the terms that were contributing to that in order to have stronger control on the calculation and on the deep understanding of the cancellation occurring there.
Now, one thing that I think is common between this aspect of looking at the virtual and trying to learn from the virtual how to deal with the real, that's the same idea that also the Torino group is using?
Okay, so if you want, do you want a political answer or? So, okay, true. So in Torino, we did some studies based on the factorization properties of gauge amplitudes. And yes, indeed, this is quite close to that study. However, in Torino, we realized that in order to apply it, practically speaking, so to implement it on a computer, we were, let's say, implementing a lot of very complicated machinery based on mappings and all this kind of structures. So there is exactly where I was saying that some schemes are very difficult to, let's say, they are very good at hiding these simplifications. So Torino is one of these examples. Although I'm one of the authors, so sorry, this is the non-political answer.
Okay, thank you very much. So any other questions to Chiara? Yes, someone.
So with these two, so what you're developing now, will it be as general as, say, a slicing approach, where you don't need to compute so many counter terms?
Well, the point is that is way, again, is not political, but in my opinion, is way better than a slicing because here it's a local subtraction. So we don't have to take any, so we don't have to control any slicing parameter.
expected to be more efficient in doing this. Yeah.
I would definitely say so.
Final questions for Chiara? Then, if not, then thank you very much.